Hi, my name is George Edwards, and I'm on the UAB MSTP waitlist, and I'd like to provide a short research update and express my intent to attend the program should a spot become available. I hope you enjoy.
This is one. It looked like a really nice experiment. Two, that one lane is everything.
Hey, this is George Edwards. I'm a research specialist here at the UNC Lineberger Cancer Center. I'm going to take you through a day in one of my latest experiments. Here, let's go in. I'm in my current preparation, about to go over to the genetic medicine building where we have our mouse vivarium. So before I go, I'll always have a sticky note ready to jot down the cage cards with the particular mice that I'm going to need. So for this experiment, I always go for mice that are roughly 8 to 10 weeks old, give or take maybe a week or two, depending on our availability. So I'm going to be using C57 Black 6 mice. I've got a sticky note with what I need to get. I have my bag for the mice and the card, so let's go. Got all 4 of the mice that I was hoping to get, so we're going to head over to the lab again, and just to briefly give you an indication of what I'm going to be doing with these mice. So we think that the tyrosine kinase receptors MER, AXL, and TYRO3, particularly MER and TYRO3, could be involved with this ERK pathway that I'm studying. So we think that there's kind of a dead cell driven pathway that could be contributing to drug resistance by tolerizing dendritic cells through a metabolic shift and how they present antigens to T cells and potentially lowering the immune response that people have. So what better way to tell whether these receptors are involved than using genetic knockout mice. Okay, so I've spent some time here getting the whole bone marrow harvest set up ready, so I'm just going to talk you through the workflow here. So essentially I've got the mice over here, which I'm going to euthanize one at a time, and then when I'm done with that, I'll be taking them over here. This is where I'm going to be sitting and working, and I have one of these pads that I'm going to be using for each mouse, and these are the tubes that, so after I get the legs out of the mice, I'll put them in the 70% ethanol just while I'm getting the other leg out, and then after that I'll clean the bones, and then each, the femur and tibia, one at a time will go in to these tubes. So what I've done is I have a 1.5 mil tube, which will ultimately collect the cells, and then I'll have a smaller tube that I poked a hole in with a syringe, and I'll have the bone that's in the smaller tube, and I'll put it in a centrifuge, and then all of the bone marrow, after I remove the kneecaps, will spin down into this larger tube, and then I'll resuspend it in some phosphate buffered saline, and then I'll put it on ice. So the first thing I'll do is sterilize both my gloves as well as the mouse so that I can keep the fur flat for a better incision surface. And I'll make the incision just in the inner thigh. I'll isolate a flap of skin off to the side for better visibility. And I'll take the scissors and spread them apart so that I can isolate the leg. And then I'll start cleaning the hamstrings as well as the quadriceps. And then once I've got far enough, then I'll actually reach in to isolate the acetabulum and pop it out of the hip socket. And then from there, I'll be able to locate the acetabulum with my scissors and then cut out the leg. Now I'm cleaning the bones so that I can separate them and put them in my tubes for spinning. I'm going to start by removing the foot by loosening some of the ankle ligaments and snipping them. Then I'm going to clean some excess muscle tissue on the quadriceps, the calf, and then also snip some tissue around the knee, including the ligaments. Then I'll be able to use the scissors and pry apart the knee and put the bones knee side down into the tubes. Then once I have the tube sealed up, I'll take it and I'll spin it in the centrifuge. Alright, so now I've got the legs out, finished, so you can see now I've actually got the marrow to clear through. Now I'm going to resuspend the cells in 500 microliters of phosphate buffered saline by pipetting up and down. So I've got this line here. These are the wild type bone marrow cells that I'm going to plate in a single 12-well plate. And I have 4 knockout cells that are just deficient of the MER tyrosine kinase. And then these 4 are bone marrow cells that are deficient of both the MER and its counterpart TYRO3. receptor tyrosine kinase. They're in the same family. So we're going to see if there's any differences in the signaling between the wild types and then knocking out MIR and MIR and tyrosine. So I'm going to be differentiating these bone marrow cells with GM-CSF, which is a type of stimulating factor. I'm also going to be using interleukin-4. Now I'm in the tissue culture room. First I'll have the note of my task on the hood and I'll sterilize myself and the equipment. So I'm going to be taking all the individual tubes where I collected my cells and suspended in PBS, and I'm going to compile them into larger conical tubes for spinning and resuspension in cell media. So I'm also grabbing waste tubes so that I can potentially collect the cells that are not effectively spun down, rather than using an aspirator and losing all of these cells. So I can actually do 2 spins and maximize my cell yields. So now I'm going to pipette each cell from the smaller tubes into the larger tubes. Now I've got all the cells collected, and I'll put them down in the centrifuge and spin. Now I finished the spin down, and I also have my plates ready for when I plate the cells. The first thing I'll do is pour off the supernatant from the spin into my waste tube, and I can immediately see that after doing this, I have a lot of floating cells in the waste, so I know I'll need to do a second spin. So I'm only going to add half of the final intended volume into my tube of current cells with the anticipation that I'll be doing a second spin. And I'll add a smaller volume for the knockout cells because I only had 1 mouse for each of these cells, so I have less total cells. Now I have my waste tube spun down, and I've created a second set of tubes to collect the second set of supernatant. I'm going to add the second half of media to each of these waste tubes, and then I'm going to combine this media with the original media from the first spin. So I'll go ahead and pipette up and down. Now I'm going to spike in 5 microliters of GM-CSF and 2.5 microliters of IL-4 cytokines to differentiate these bone marrow stem cells into CD11C positive dendritic cells. So once I have that done, I'll mix the vial, and then I'm going to just plate a single well with 2 milliliters of this media. And then after that, I'm going to go over to the microscope and verify that nothing funky happened to the cells. And I can see that there are cells here. Then I'll finish the plate, put it in the incubator for maintenance every 2 to 3 days over the next week. I'm just finishing up the bone marrow harvest from today, and I think it went really well. It was a very long afternoon, and we're finishing up here after dark, but I think the cells are going to differentiate well and be hopefully in good yields for next week's purification and treatment. So I really enjoy doing this bone marrow procedure because it kind of is like a first little taste to surgical operations, which is something I want to be doing a lot someday. I'm really interested in orthopedic surgery as well as surgical oncology. So I think it's a good test of kind of building up the mental and physical stamina that you need to be successful in every moment in those critical situations. And I think that's something that you can't really test on any sort of exam. You just kind of have to build that up over years of gaining proficiency. And in my case, I never really learned that through any sort of academic textbook, but I've actually learned that doing real-life research experiments that could potentially benefit people. So that's really why I'm interested in being a physician scientist. It's been a week of differentiation, so let's go purify and treat the cells. So the first step of the purification is to remove any dead cells that may still be present in the mix of dendritic cells, because we're going to be experimenting with the treatment of dead cells, so we want to make sure that our baseline cell population is dead cell free, or at least as close to it as we can get. So to do that, I'll be using a stem cell magnetic dead cell separation kit. So I have a special dead cell buffer of calcium chloride that I'll be using, and I'll also be adding a small amount of the Nexin-5 and biotin markers that are often present on apoptotic cells, and then the dead cells will actually be pulled to the outside of a polyethylene tube. One of these counting channels, and I'll always make sure that I've got all of my liquid in and that there are no air bubbles present in the film area where the cell counter will be operating. So in this case, it looks like I've done a good job, so we're going to kick it over to the machine, and we'll see how many cells I have. So we can see that I've got a little bit over 1 million cells per milliliter, and I've got about 36 milliliters total. So I've got a little bit over 36 million cells that I'm working with for the wild types. I will do a quick calculation based on our stem cell protocol of how much dead cell buffer that I'm going to need to add based on the number of cells that I had. So off the 36 million wild types, I need to get those cells to a concentration of 1 times 10 to the 8 cells per mil. So in this case, I'll just be adding 367 microliters of my buffer. Biotin marker. In. Now go straight into the magnet. 3 minutes, lid's off. Straight in, start the timer. So I finished doing the dead cell removal with the Easy Set magnet, and my cells are now spinning in the centrifuge so that I can do a CD11C positive selection using another stem cell kit, and I'll be using the column buffer for this particular selection and components that are labeled A and B, which are selection cocktails for the CD11C positive dendritic cells. So I just want to do a quick explanation of how this selection works. So essentially this selection cocktail has components that will adhere to a CD11C positive dendritic cell, and the copper beads in this kit will adhere to these special components, and then the actual magnet will suck out the copper beads to the outside. So my cells will be on the outside of the tube. So I finished doing the purification for CD11C and dead cell removal of the wild type dendritic cells. I ended up with 10 million total cells, which is plenty, and more than the 6 million required cells that I needed for treatment. So now I'm going to plate those cells and repeat for the other 2 cell lines. So I'm going to have my treatment conditions in 2 12-well plates. So think about this as 3 sets of 4. And I'll have my wild type cells in the first well, and then I'll have wild type and dead cells. Then I'll have the MER knockout cells, spiked with dead cells, in those same conditions twice more. But the middle set will always have one particular ligand to the receptors, protein S. The last set of 4 will have Gas6, another ligand with more of an affinity for the axle receptor. And the second plate is laid out the same way, but instead of MER knockout cells, I have a MER tyro double knockout cells that'll be in these 6 wells. When we look at the wild types versus the freshly plated cells, there's a very clear difference not only in the media color as the cells are using the media and the contents, but also just giving a slight shake to the plate will show that the wild types have largely settled at this point, but there's actually a moving layer of unsettled cells in the freshly plated cells, as we would expect. And I have a couple vials of tumor cells, the GEM6 line, that I'm going to be freezing down as a way to induce death. So I'm now thawing those cells, and I'm going to remove the cryopreservant that is currently in these cells by spinning down and removing the media. I now have my GEM6 cells thawed, and these are actually a murine melanoma cell line that I will be using as the sort of standard dead cell treatment. And from our experiments, these seem to be a reliable cell line that are pretty representative of the dead cells that could accumulate in a tumor microenvironment and potentially impact somebody's response to a drug. It's been about an hour since I plated the purified dendritic cells for the 3 cell lines, and I made sure that my cells have settled to the bottom of the plate, which means they'll be ready to treat with dead cells and ligands in the supernated medium. So I prepared a 1 to 10 dilution of the Gas6 ligand that I'm going to be using to treat, and I'm currently thawing my dead cells, and I'll be spinning those down and resuspending in a short volume of media, and I'll be able to spike in 10 microliters to each of the conditions that have dead cells. Just done my first set of treatments on my first plate, and 15 minutes is up, so we're going to aspirate the media from each of those wells in the 12-well plates, and then I'm going to add my lysis buffer that I freshly made, 100 microliters to each well, collect it in a tube, put it on ice, freeze it down overnight. Let's do it. All right, so I finished lysing and collecting the first plate of cells, so I'm going to go ahead and freeze them at -20, and we'll work with them tomorrow. All right, so I finished the treatment and the lysing of the cells today. Finishing up here about 1 in the morning. It's the latest that I've ever spent in the lab, but it was a long procedure because I had to repeat the purification for 3 different cell lines. So that was really the longest part of the experiment, and it definitely took a lot of physical and mental stamina to get through today, but I think I managed really well. There were a couple of moments where I had to improvise a little bit along the way, but that's completely normal as I've learned in a research setting, and I think will serve me well in medicine. A few moments I think about are how I had to make a fresh lysis buffer. I did a 2-part treatment with my protein S, and I also had to decide how many times I wanted to do a CD11C selection. So I'm really looking forward to the data that I'm able to get with Western blotting over the next few days. I'm hoping to see some interesting results with regards to the MER and tyro3 knockout cells in terms of lowering the phosphorylation of a couple proteins I'm going to be looking at. And we'll be interested to talk with my PI, Shelley Earp, over the coming week, and potentially get a chance to speak with Eric Ubel in the Department of Immunology at UAB and get his thoughts. And potentially, if MER and some other tyrosine kinases are involved in this pathway, a logical next step would be to collaborate with Eric and try using one of his PTP1 inhibitors, BVT, that he's been using in his experiments. So I'm really looking forward to what's to come, and at the end of the day, I need to realize that this is only the first time that I've done this experiment. So either way, the results would need to be repeated before we come to any definitive results, but I'm going to live with the results and take them for what they are. We'll see you in a couple days. We're here a few days later first thing I've done is I've thawed and spun down my lysates, and I'm going to boil them for 15 minutes in a heater so that I can denature the proteins to their primary sequence so that they can be more easily imaged and flow through the Western gel. So while my lysates are boiling, I'll go ahead and I'll prepare my gel interface. So I've clamped in two 10% 15 well gels, and I've poured in a MOPS running buffer solution up to the 2 gel mark and also between the gels so that I'll be able to nicely load in my lysates a gel at a time. It's a day later and we'll be imaging the Western blots. The first step is to wash away any primary antibody that hasn't bound to the membrane. Then I'll be adding an anti-rabbit secondary antibody, which is conjugated to horseradish peroxidase, which is an enzyme that will oxidize luminol in an enhanced chemiluminescence reaction, emitting light when exposed to 428 nanometers. The more protein that I have, the stronger the signal will be as more of these reactions are taking place. So I've just finished imaging my Western blot, and I've prepared a PowerPoint slide to summarize the results. So you can see that I've broken up these two images, the top image being the blot that has the last conditions being the MER single knockout, and the bottom image having the last wells being the MER and Tyro3 double knockout, in such a way that is broken into 6 sets of 4, where in the first 2 columns of each set of 4, I'll have the wild-type bone marrow dendritic cells, with the second column having dead cells, and then the last 2 columns of each set of 6 will have a knockout cell line, again with the second column being spiked with dead cells. The sets of 4 that are closer to the right side will have protein S in the middle set of 2, and then the Gas6 ligand. And it's very obvious that having these ligands added is enhancing the phosphorylation that we're seeing from dead cells on phosphor work significantly, whereas without the ligands, the effects are much weaker. What really stands out to me is this particular well where we can see how protein S alone actually leads to a great phosphorylation when MER itself is knocked out, whereas all of the other lanes that have dendritic cells of any cell type in either ligand generally show a weaker signal. So what I'm thinking is potentially this pathway is more dependent on the Tyro3 receptor, and the MER receptor could actually be serving to counter the effects that its counterpart receptor could have. So in the future, I think it'd be really interesting to look at this experiment when looking at other antibodies in this pathway, such as the MEK antibody, and then also experimenting on different types of knockout mice to see, well, what are the effects when you potentially knock out the AXL receptor. So those are some directions I think we could go, and obviously we need to repeat this experiment. But so far, I think this experiment has really shed some light and given some great direction on where I need to go from here in publishing this paper and solving this pathway. Okay, I definitely am seeing some effects here with the ligands being added in. And the second thing is I really want to just point some attention to this particular well in the MER knockout, because this was really the only condition in these 2 images where I saw very strong phosphorylation in a condition where there was just one of the dendritic cell subtypes with one of the ligands, in this case, protein S. So I'd really like to get your thoughts overall.
This is one, it looked like a really nice experiment. 2, that one lane is everything, and that's why it would need to be repeated. So the obvious way of thinking about this is that the MER knockout bone marrow derived cells have Tyro3, and that can do this by itself. Whereas down below, you don't see this when you have the MER Tyro3 knockouts. Right. So that's, if that's repeatable, then we would we'd have to conclude that protein S can work alone through Tyro3 in the MER knockout cells.
Right.
Okay, right. Good. Okay, see you everybody.
Bye. Thank you for watching. I hope this video shed some light on my potential to succeed at your MSTP program. Hope to see you in the fall.